Welcome back. This video takes you through the quick heat gain process for calculating daily heat gains that will be used to calculate the night-cooled mass system. So I'm going to go right over to the P2 Quick Heat Gain tab, and here we are looking at the worksheet for quick heat gains on a daily basis. So we'll use this quick method to estimate the daily heat gain that has to be stored in a night-cooled mass system. Night-cooled mass is useful in many climates where the daytime temperature is too hot for natural ventilation. Say for me that might be about 85 degrees, and for somebody else it might be cooler. It's also useful where the night temperature drops cool enough to open the building to ventilate and cool down the mass at night. Now, up here on the top of the page we'll see the design guideline for night-cooled mass, and this tells us when the building might be opened and when it might be closed. Remember that it's closed when it's too hot outside to ventilate, and it's open when it's cool enough, typically at the bottom of the comfort zone or below the comfort zone, so that we can bring in outside air at relatively high volumes to cool down the mass in a few hours. So the rule says if the outside maximum temperature is 100 degrees, then close the building between 6 a.m. and midnight, or about 18 hours of closure. If the maximum temperature outside is 90 degrees, then close the building from about 8 a.m. to about 10 p.m. for about 14 hours of closure. Since this example is in Knoxville, I'll choose 14 hours of thermal closure. So I'll go up here and input 14 hours. I also need to input the number of occupied hours. Since this is a residence, I'll say that people are home from about 6 p.m. till about 8 a.m. for a total of 14 hours. So 14 hours of thermal closure, 14 hours of occupied hours, except these two periods are actually not the same clock hours, but they do overlap. In Part A, the rates of heat gain for occupants and equipment carry over from the hourly calculation. All we have to add is what percentage of the occupied hours are fully occupied. I'll assume that on average everybody's home for about 14 hours a day, so I'll use 100%, which just leaves it right at the default for 100%. Remember, this is relative to the assumptions that you made previously about the number of occupants. For equipment, however, I'll assume only about 6 hours of use, since they'll not be using much of the equipment or appliances while sleeping. So 6 out of the 14 occupied hours they're awake, or about 43% of the time. In Part B, electric lighting gains, we need to make a few more assumptions. Given the summer month that we're designing for, how many hours of usable daylight for daylighting could we have, and how many hours will we actually be using in the building given the occupancy period? So let's take a look at the climatic context report for Knoxville. Here's the section on daylight availability, and we can see the illuminance calendar here. And if we look at this illuminance calendar for Knoxville, we can see there's about 11 to 13 hours of substantial daylight. For example, in August there's good light, that is over about 500 foot candles, for about 12 hours. But since this is a residence, I'm going to assume that an hour of daylight might be used in the morning and 2 hours at night for a total of about 3 daylighted hours. Alright, so we'll close that. Come back in and look at 3 hours of daylighting use. And if we give them about 8 hours of sleep, then there'll be another 3 hours of electric light use. So our total lighting use hours is 6. Now, if you're designing an office building, these inputs would be totally different because the occupancy schedule would be different. Now remember that from Part B on the table for electric lighting heat gain for residences, we found that with no use of daylight, the rate of heat gain might be between 0.7 and 4.1 for very efficient to average lighting. And again, splitting the difference, I'm going to put in about a rate of 2.4 for the night rate. So we have a night rate for when electric lights are used without daylighting, and then that gets reduced and calculated with a different rate for the number of hours when daylighting is used to give us a total daily heat gain rate. from electric lighting. In part C, heat gain through the envelope, we only need to add the number of solar gain hours. But again, we need to have some basis for doing that. So again, let's go back to climatic context report. And our radiation is found on page 7, so I'll just go straight there. And here's our radiation calendar, so the same format, 24 hours by 12 months. Most of the heat gain comes during the period of the day when the building is closed and the sun is out. So looking at this radiation square, we see there's roughly about 9 hours of radiation in the category over 100 BTUs per hour per square foot, which is the value I'll recommend for solar gain hours. So I'll go back and input 9 hours. So back on the quick gain sheet, the number of solar gain hours, about 9. In part D, for ventilation and infiltration, we can keep the percentage of hours fully occupied the same as the occupants above, or we can change it. If you've not used mechanical ventilation in the quick heat loss worksheet, then definitely set this at 100%. If you plan mechanical ventilation without occupancy schedules or variable rate controls, then again use 100%. I'm going to assume a simple system and leave it at 100% for the example project. The total daily heat gain then is the amount of heat that must be stored in the thermal mass during the thermally closed hours. The result is used in calculating the P2 night cooled mass worksheet, or it can also be used in the nomograph tool in the sun, wind, and light night cooled mass design strategy. If the heat gain is too large to be stored in the mass, then you can examine the individual component loads and redesign to reduce the gains. This might mean, for example, better shading or more use of daylighting. It could be more efficient lights or better equipment, or better insulation, looking back at the skin thickness strategy. You could be reducing your window area to reduce the amount of solar gain coming through the windows, or employing other kinds of strategies that might reduce the solar load, like double skin materials. That's also a strategy in sun, wind, and light. You could employ air-to-air heat exchangers, earth-air heat exchangers, airflow windows, or any of a number of strategies that might reduce the load of the incoming ventilation air. And all of these can be found in the sun, wind, and light design strategies. Well, that's all for this topic. In the next video, we'll take you through looking at solar apertures and find the building's solar savings fraction.